and we're going to be studying function analysis analytically. And more importantly, today we're talking about increasing and decreasing work. So there's a lot more to talk about in terms of function analysis. Like when we talked about things like speeding up and slowing down with particle motion. And that'll be saved for Thursday. But we're going to be doing this analytically, and just like with particle motion, after we do things analytically, we'll do them graphically. And you should find that to be relatively easier when we actually get to see the graph, because most of what we do is based on the graph. I just prefer to start with some analytical work. The longer you can work on the problems analytically, I feel the better you'll be overall. Even though maybe graph might be a little bit easier intro, I think we can handle it and do it this way. So we're going to be talking about now. I want to note that y equals f of x, y equals f prime of x, and y equals f double prime of x. These are all, first and foremost, these are all functions. All right. They are individual, they are functions on their own. Right? So when I talk about the f of x function and f prime of x function and f double prime x function, they are functions on their own. I could ask you what is happening with f prime of x or with f double prime of x. But it should be noted that f prime of x and f double prime of x, oh, sorry, let me write it. F prime of x also describes increasing / decreasing behaviors of f of x. So from f prime of x, we can describe what is happening with f of x. And this is a very important thing, because to do these analytically, now if you had the graph of f of x and you were looking physically at the graph, in most problems it's very obvious what is happening. We utilize f prime of x to find exact changes in behaviors rather than just eyeballing the f of x graph. You never want to just try to graph it, because there's little subtle changes that happen where if you were to graph it in your calculator or Desmos, however you're graphing, the function might look like it's going up, 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 up. But if you were to zoom in, you might see that, wow, it actually goes up and then down and then back up at certain spots. So it's like a little bleep. And it's those little parts that are very important for us to understand and to utilize and to analyze. So as I also noted, there are going to be many features. So basically, the questions are going to be most all AP calculus questions ask about the behavior of y equals f of x given / utilizing y equals f prime of x. Rarely, and I say rarely because it's not always, okay? It's not always, and I say most all because sometimes you are actually asked about the behavior of the derivative f prime of x, stuff like that. Rarely are you asked about f of x given f of x graph. So it should be noticed that for almost all the questions, if they're asking you for these type of behaviors, means that you have to find and analyze f prime of x or f double prime of x, which we'll cover a little bit later on. So we just want to make sure that if I say, hey, when is the function increasing? When is the function f of x increasing? It's calculus, okay? So remember, this is calculus. So you're not just going to look when something is increasing and go, oh, the graph is going up, therefore that's my answer. No real calculus in that question. Now, I have seen questions where they do something very similar to that on a multiple choice type, but there are slight variations. Rarely have I, but those questions, they gave you f of x and they kind of just reversed the question. So they gave you f of x and then they ask about f prime and f double prime. That's slightly different. So in calculus, we're never really going to, at least testing wise, we're never going to be asked about the feature of a function given that specific function, or at least in the graph. And to do the work and to prove, because a lot of it's about proving, making sure that this is the answer, there is no other answer. And to do such, we have to be able to utilize the derivative. Here is a graph of y equals f of x. Now, once again, notice that I do not have any scale, x and y scale like 1, 2, 3, 4. So we don't know where things start changing. We can eyeball them, of course, but that's not the purpose of what we're doing. But if we were to look at this graph, I could see that this graph is increasing over these two intervals. F of x is increasing here, and f of x is increasing there. So talking specifically about the function. Now, like I said, this isn't a question that you're going to be asked, but it's something that we need to identify. And the function f of x is decreasing on that interval. Now, there is something, like I said, there's things about concavity we'll get into, but today and tomorrow, we're just focusing on this increasing, decreasing behavior. So that's given the graph of f of x. Now, when we talk about the function increasing or decreasing, the question is, how do we identify when a function is increasing versus decreasing? Well, the answer is in the derivative. So it is noted that f of x is increasing when what? What could you tell me about that is true about that function when the function is increasing? How do you know a function is increasing besides it going up? What could you tell me? Somebody chime in here. What can you tell me about a property of the graph when that function is increasing?
Is it when your velocity means zero?
So that's the we call not analogy, but it's similar to that idea. But without using particle motion terminology, if we were asking, think about if you were like in the ninth grade, and I say, hey, this graph is increasing, this graph is going up. What is the mathematical um, idea that we utilize?
Slope.
Slope. Very good. And what would you say about the slope?
The slope is positive.
The slope is positive. All right. Now in calculus, so in calculus, what tells us slope of a function? What is the slope function?
The derivative, so f prime.
Perfect. And as Ariana said before, with f prime of x is positive, greater than 0. And similarly, a graph is decreasing, a function is decreasing when f prime of x is what?
Less than 0.
Less than 0. What this means is that we're going to need to do some sign analysis in this, just like we did before, which means we will need to create sign charts of f prime of x. So we'll need to create a sign chart. We'll need to answer questions like when is the graph increasing, what is the graph decreasing, and so forth. Now, we could look at values of the derivative and say, oh, if so, i.e., if f prime of 5 equals 6, then this means that f of at x equals 5, f of x is increasing because the derivative is positive. So at that point, now in these topics, now you might get a multiple choice question that asks specifically at a point. We don't get those questions very often. Most of the times it's going to be asking about finding intervals. Example, f of x equals 3x squared plus 5x minus 6. Find when f of x is increasing and decreasing. Justify. All right. Yeah, you know what? Let me just bring this down into the other page. There we go. All right. So think about the process that we do on these other ones. If I ask you about increasing, decreasing for a function, the first thing that needs to come on top of your head is what?
Take the derivative of f of x.
Yeah, so find f prime of x is basically step 0. Sometimes you're actually given f prime of x, okay? And I want you to note that. So sometimes in problems, I give you directly f prime of x, and then I ask you. Now, we do these more for maybe some more complicated functions that might be hard to factor. The good news is, like in today's work, I'm basically going to be giving you problems where there are polynomials and it's f of x. So tonight's problems, I'm giving you f of x, and it's a polynomial. Tomorrow, on the homework handout, I'll give you some problems that are very similar to that, but I'm also going to give you some problems where I directly give you the derivative. All right, so just to note. So that's why I call it step 0, because sometimes you're given f prime of x to start. All right, so f prime of x equals
6x plus 5.
6x
My
plus
bad.
yeah, 6x plus 5. Now, the good news here, and something that I didn't really bring it over, I didn't talk about in these problems, but there is um, usually no domain restriction. And mostly I'm talking about polynomials on this case. So when we were doing particle motion, we did things like instead of x, it was t. And I said t had to be greater than 0 because it doesn't make any sense to have negative time. That's not the case here. So there's going to be negatives. We're going to go from negative infinity to infinity. And our intervals don't start at 0, so we don't have to chop it up. It's actually easier. Now, our goal here, so step 1 would be to what? What do we do after we find the derivative? We find, and actually this is a new vocabulary word. I know you know probably the process to do. What do you think? Well, let me hear you out. What are we going to do mathematically once we find a derivative?
Are we doing the sign chart?
But before we get to the sign chart, what is our next step? You found a derivative, and it's the same process over and over and over, which is really helpful. After we find a derivative, we do what to that derivative? When you found velocity, what did you do with the velocity after you found it?
You take the derivative of the velocity
No, that's not what we did.
after you found it.
So velocity is like the derivative. So once we found the derivative, what do we do? And it's the same step basically all the time. And when we're doing this work analytically.
Do we do 6x plus 5 equals 0?
This equals 0. Very good. So we find what we call the critical points. We do that by taking f prime of x and solving f prime of x equal to 0. All right, and it's always the same. You always take the derivative and equal to 0. All right. Now, when we find these answers, they're technically called the first derivative critical points, but in calculus are the first derivative critical points. We just call them the critical points. All right. All right. That's pretty easy math, right? It should feel comfortable in terms of the math that we're doing here. So we get -5 minus 5. We get 6x equals -5. Divide by 6. We get x equals -5 over 6. Now this is the critical point, and it's only one. So a lot of times you're going to get 2. So you're going to have to do some quadratic factoring maybe when you have to do the problems, which I'll do for our next one. But most of the time, sometimes you get 1, sometimes you get 2. Step 2. After we found our critical points, what do we do then?
Now we do sign analysis?
Yes, now we do the sign analysis. So step 2 is now we do the sign analysis, which we refer to as the sign chart. You should feel very comfortable in terms of if the process stays the same. Take a derivative, set equals 0, solve, make a sign chart. So and negative 5, 6, and this is f prime of x. So now there's only two intervals here. Remember, negative infinity is furthest to the left and positive infinity is furthest to the right. All right, so there's two intervals here. Now, some people like to place where 0 is on the interval. You don't really require to place 0. If you feel comfortable doing that, just recognize that it's not a critical point. And f prime of x is 0 right here. Okay, I like to put that at 0. Now we need to find what is the sign. Now there's a couple of ways we can do, and as I taught you before, you can do the same method. There's the plug-in method is one of them. Basically what you're doing is, here is my function derivative, right? And so if I were to graph 6x plus 5, 6x plus 5 would look like this. So you should be able to see as a result, when is on the first interval, is f of x, is f prime negative or positive over here? Which one is it? For all these values over here, is the graph of f prime negative or positive?
Positive.
Well, look at the graph. It's below.
No, negative.
So it would be negative. Now you can do it like this, or you can write. I like to do my sign charts. Sometimes either way it's okay. So I like to do. I'm gonna do minus signs this time. It's the same thing if you want to write the word negative, neg. And what about the other side?
Positive.
Positive. Oops. Now you can see that by looking at the graph. However, maybe that doesn't work for you. Maybe that doesn't work for you. We always have the option of plugging values into f prime. For example, over here, negative 1. Over here, 0. So if I find f prime of negative 1, and I use that in a calculator, I get negative 6 plus 5, which is negative 1. Which is negative, which means that entire interval has to be negative. Because the only time it can change is when you cross a critical point. If I find f prime of 0, I get 0 plus 5, which is 5, which is positive. So just like we found our sign charts, however you felt most comfortable, there is no you have to do it this way. Now there's ways I recommend in doing it. A lot of the students who spent the time with me over the summer will probably do their function analysis using things like the multiplicity a little bit more, or maybe they feel more comfortable because they spent multiple weeks covering that type of material. Where if you don't, some of you might have clicked and had gotten that, and if you don't, just plug in a number. For the most part, you have access to a calculator. Depending on, from my understanding so far, is that all I've learned about the AP exam so far since the last time we talked about it is that all the materials on the exam, they're not taking anything off. With that said, they haven't said the layout of the exam yet. All I know so far is that all the material is fair game. All right. So f of x is increasing when?
Isn't it negative 5 over 6, comma, and then positive infinity or infinity or something?
Yeah. And f of x is decreasing when?
Negative infinity,
Mm-hmm.
comma, negative 5/6.
Perfect. Oh, and I didn't state why. The reason over here is because f prime of x is greater than 0, and decreasing because f prime of x is less than 0. Don't forget the justifications. You must literally just say that. You're like, well, but you can see I showed you that in my sign chart. On the AP exam, they do not accept the sign chart part. We want to know directly you stating that reasoning. Okay. Relative extrema. When I say relative extrema, it's actually we're referencing two different words. Relative minimum, sorry, and relative maximum. So we say the word extrema in the sense that we could be talking about relative mins or relative maxes. Most problems will just ask you to find the relative extrema because we don't want to say find the relative minimum and the relative maximum. Some problems do, but rarely do they say both of them. We also say find any relative extrema because we don't want to tell you specifically if there's a min or a maximum, a relative min or a relative max. Some questions on the AP exam will state questions simply as, how many relative extrema are there? And then you have a multiple choice, 1, 2, 3, 4, 5. Some questions will say, find and identify the relative extrema. Basically, whenever a question asks you to find relative extrema, especially when it's analytically short answers, you should always note when there's a relative minimum versus a relative maximum. A relative minimum occurs at the bottom of a graph like this, and a relative maximum occurs at the top of the graph. Anywhere on an open interval. Now, when we say the word relative extrema, also known as local extrema in some textbooks, not ours. And on the AP exam, they use the word relative versus local, but you might hear somebody say local and they're not wrong. They are synonyms, relative and local. And the idea is that relative to the points surrounding the output is a max/min. Think about it sports this way, or even school. So at BCLA, we have, let's say basketball. There's the best player. Okay, they would be the relative maximum. All right, they are the best basketball player at BCLA. Does that mean they are the best basketball player there is? Question? No, they're just the best. They're relative to the players around them, relative to the players at BCLA, they are the best. But if they might be better than the best player at some other schools, but they might not be the best player. Now, could they be the best player? The answer is yes. And we'll get to that later on. To be the best player, period, in high school, in Boston schools, you need to be at least the best player relative to those around you. All right. But there could be many best players relative to their team, their location. All right. We call these relative extrema. In those cases, the case that I just said, relative maximum. Now, I want to give you the formal definition. Or, actually. So how do we find it? Now, this is called the first derivative test for relative extrema. It says, and I'm going to give you the formal definition, and I'm going to give you the kind of layman's one that we just used. The first one says, and this is important, if f of x is continuous on the interval, on the closed interval in this case, a to b, and actually, hold on. Yes, if f of x is continuous, I'm just gonna go with the layman's one. If f of x is continuous on the interval a to b, then f of x has a relative max at x equals c, given that f prime of x changes from what? What is f prime x going to change to? You've reached the top point right here. So if we look here, what is f of x doing here? And then it changes to here.
Decreasing.
So, but changes from, what is it doing first?
Increasing.
And then?
Decreasing.
Okay, so what is the derivative doing? The derivative changes from?
Isn't it the same thing?
No, it's positive to negative. F of x changing from increasing to decreasing. But we have to describe it in terms of the derivative. You must describe it in terms of the derivative. So f prime of x changes if f of x is continuous on a to b, then f of x has a relative min at x equals c, given that f prime of x changes from
Positive to negative?
no.
Wait. Isn't negative to positive?
Negative to positive. F changing from decreasing to increasing. Now remember, your justification needs to be the actual about the derivative. Now something to note, the relative max slash min is the output value, f of c. All right. AP exam may ask for the relative min slash max, or the x value or values where they occur. Because it basically, you have this coordinate c f of c. This is where, and this is the what. Sometimes the question will ask you where does it occur, and that's when we do intervals. Find the x values where, or sometimes they'll say what. What is the relative min? What is the relative max? And that's the output. You just find that by plugging back in the value. Questions? We'll do one last example and we'll call it a day. Okay. Example. F of x equals 1/3 x cubed plus 3x squared plus 8x minus 6. Find all relative extrema. Oh, so actually let me do it more like the 8 question. Let me do it like the homework question. Find when f of x is increasing slash decreasing in all relative extrema. Justify. Okay. So these questions, and typically to find relative extrema, you have to find when the function is increasing, decreasing. So basically, let me just go back to this previous problem. Is there a relative extrema on this previous example? Yes or no?
No. Yes.
Well, I'll just wait for somebody else to chime in. I want to hear at least 2 responses. Is there a relative extrema on that, using that sign chart on that one right there? The answer is yes. The derivative is negative, and then the derivative changes to positive. So not only is there a relative extrema, there's a relative minimum on that problem, because the derivative changes from negative to positive. So we're going to do the same thing. Increase, it goes from decreasing to increasing. So technically the graph, what the graph in this problem is doing, and I didn't really note this in the previous one, but what the graph is doing is the graph is decreasing, and then it changes to increasing. So the graph looks like a parabola, and it is a parabola because if you looked at the original equation, it was 3x squared, which is a concave up parabola. And so the graph is going down, 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 down till x equals negative 5, 6, and then it's going up, 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 up after that. Like I said, don't worry, we're going to be spending quite a while. We're just doing the analytical, almost memorizational type stuff today. So, first steps are always the same. So what do? If I hear increasing, decreasing, relative extrema, these all tell me function analysis, I should?
Find the derivative of the equation.
Perfect. And my derivative is?
X plus
Up.
6.
Up.
Oh, x squared
Mm-hmm.
plus 6x
Mm-hmm.
plus 8.
Good. And then what do?
Equal to 0.
Perfect. How do I solve this?
Factor form.
Factor, good.
X plus 4, x plus 2.
Good. What do I get?
X equals negative 4, x equals negative 2.
Good. What do I do with these values?
Sign chart, or yeah, sign chart.
Mm-hmm. All right. How do I find... Now remember, there's 3 intervals now in this problem, and each interval is either entirely positive or entirely negative. Now, what you can do is, if you feel comfortable, like I said, if you feel comfortable, you can say, you should know what x squared plus 6x plus 8 kind of looks like, right? It's a parabola that opens up. So basically, the derivative looks like this. And since you know the derivative looks like that, then this function, then the values of f prime are going to go from what to what to what?
But is it gonna be aren't the ends gonna be positive because it's a square, and the middle is gonna be negative?
Correct. So if you look at this derivative, that's what it looks like. And so it's going to go from positive above it to negative to positive. If you don't feel comfortable doing that, then you can pick some points inside here, and you can find f prime of negative 5, f prime of negative 3, and f prime of 0, and you will get something that's greater than 0, less than 0, and greater than 0 again, if you want to just plug it in using something analytically. But if you want to just graph f prime on top of your sign chart, and for these ones, like I said, they're not going to get any harder than these ones right here for now. It's the same way we did the function analysis for the other ones. Now, because the derivative changes from positive to negative, what do we have right here, right between? What do we have right here? The derivative changes from positive to negative. So what happens at negative 4? The derivative changes from positive to negative.
Wait, when it's at negative 4?
Yeah.
Isn't the slope 0?
It's a relative max.
Oh.
And over here at x equals negative 2, we have a relative minimum, because the derivative changes from negative to positive. We're going from negative slopes to positive slopes. So what's happening here is that what's really happening here in the graph, if we were to talk about what is happening for f of x, basically f of x is going up, then f of x is going down, decreasing, and then the graph is going back up. This is what's happening with f of x. So f of x is going like that, and then like that. And so we have a max, and then we have a min. That's what the graph is doing, because positive derivative means positive slopes. So it's going from positive slopes to negative slopes. To answer these questions real quick, we got 1 minute. The function is increasing when? When is the derivative negative?
0 to negative 4.
No.
Increasing.
Negative infinity to negative 4. Remember, negative infinity is always over here. Positive infinity is always over here. Union
negative 2, positive infinity.
Decreasing
negative 4, comma negative 2.
Good. We have a relative max at
negative 4.
x equals, make sure you say x equals in these cases, just to be careful, because f prime changes from positive to negative. That's the justification. And finally, we have a relative min at x equals
-2.
Because f prime changes from negative to positive. And those are the answers. And that's how you're basically, you have two, like I said, the problems are going to be very similar here. You don't have to do the justification tonight because of the fact that it's delta math. You might have to do some intervals type of stuff, but you might have to do this work on the side. But this is what a typical problem looks like. Find a derivative, set equal to 0, find the critical points, make your sign chart, and then from that sign chart, we just need more practice finding the answers. I'm sorry for being a minute over. We started a little bit later than I anticipated. Welcome back to school. Let's get going. I will see you guys tomorrow. Tutoring course with Eric today at 2:30. Take care, everybody.